So you can do both. And I think the more you get prepared for the internship questions and the interview questions, the better your choices will be to make those big bucks, which all of you are after.
Thank you, Nimi. And of course, I already mentioned Jian. He will be here on Saturdays during the mock competition time, which is 12 to 5. So we set up a mock competition. It's online. You could actually sit at home and do it. But if you come here, you get the added benefit of a whole bunch of other people who are also trying to solve the same problems. And then Jian is here, and you can talk to other people so that you learn. And you probably already know this. You learn a lot more from your peers than in class or from your professor. And and that's part of what we're doing. We're trying to build a community of skilled students. The other thing, Nimi mentioned sprinternships. That sprintership program again told us the same thing. It told us that students, it's not an easy direct path to these big software companies. You need some stepping stones before you could go work for them. And a sprintership is a short internship, which kind of helps you to prepare for a real internship. And so these, and then Breakthrough Tech and Nimi will train you before you even go to that short internship. And that kind of training is not something you can buy anywhere else. So these are all amazing opportunities. It would be great for you to go and grab these opportunities as best as you can.
Can I just add one more thing? So I want to say that on day one, we've seen a lot of people show up and then people just drop off because they think, oh, I am too, I don't know, you can fill in the adjective. I'm too this, I'm too dumb, I'm too beginner to do this. But I would say, even if you are, that's okay, because when you come here and you show up every week, things will start making sense. But don't give up before that, because it's like training for a marathon. I can't decide today and run a marathon in a week. If I have 6 months, yes, I can plan for it. So you need to start prepping for these interviews from your freshman year, not from your senior year. So
well, even if you're a senior here, it's okay.
It's okay, better late than never, right?
Right.
But you should not be intimidated by anybody or anything. And Dr. Giri was absolutely right. You can stop him, ask questions. So don't want to treat this as a formal thing, but it's informal learning, community-based learning, and it is what you make out of it. But I can tell you that these are the skills the employers are looking for. So.
And if some of these problems that we talk about here, as she said, if they are intimidating, there is a session, most likely, this
Fridays.
is set for Fridays at 2 o'clock.
2 o'clock.
Which may be a little gentler introduction to problem solving. You may want to consider attending those as well. And then we are also contemplating a Saturday session. Dr. Irvine, we're still in discussions about the format and the time, but that's something that could happen as well. So lots of opportunities. None of these are in the books as regular courses. They're just there for you to take advantage of as best as you can. Got it? Then I did mention the programming competition. I'm quite serious about it. I would like to like for us as FIU to field a whole bunch of teams. These programming competitions, how many of you have done this in your high school years? Okay, there are a couple, 2, 3. All right, good. That's great. So you know what it's like. For the others, these are intense 5-hour competitions where you get something like 10 problems thrown at you. You form teams of 3 and you sit in a room where you have no access to internet, but you have access to one computer. And the 3 of you need to figure out what these problems are about, find a solution for them, code them up, get your programs to work, and submit it, and get the problems accepted by the system. And the more problems you solve, the better your ratings are. And there are Just at FIU, we'll probably have about 25 teams. And if you look in the southeastern region, we usually have about 200 or so teams. If you look at all of US, there are probably a few thousand, no, about 1,000 teams, if you include all the regions. And then every country in the world has its own little competition and its own region. So this is a worldwide event. If you do well in the southeastern region, you go to the nationals. If you do well in the nationals, you go to the international, the world championships. So these are fun. You become an instant star if you do well on these things, and there'll be companies after you. It's that big a deal. So I do like to train students for this. Our teams have done well, but not spectacularly. But that doesn't necessarily deter me from doing this. This is more of a voluntary activity that I have for identifying and nurturing talent here at FIU. That's the whole goal here. Okay. Overall, all my Thursday sessions are very similar in nature. I will present you a bunch of problems. We'll sit and think here together, and you guys will help me solve it. That's the general format. Are there any questions for me?
What are the language they solve?
Right. Good. So remember, here we only talk about algorithms and problem solving, nothing in concrete. It's all in abstract. On Saturdays, there are the mock competitions. That's where the rubber hits the ground. You actually go and write code. You actually submit it. Make sure that it gets accepted. So there are lots of skills related to programming that you're not learning here. Hopefully you're learning it elsewhere. Hopefully you'll go to the Saturday competitions. You'll learn by trial and error. You will also have learned some from your classroom. There are debugging skills. There are other kinds of programming tricks. All of these can happen at these Saturday sessions. The way the competition environment is set up is quite interesting. There is a portal called VJudge, where I will send you instructions for how to register to VJudge. Once you register, you will have access to what's called as a repository of online problems, and there are literally thousands. There are like 10,000 plus problems there. There are something like 30 different sub-portals. VJudge is it kind of aggregates a whole bunch of other portals. In particular, it also aggregates Catus and some of the others that you may be familiar with from before. So you will have access to problems. You can pick any problem you want. You can write your program and then submit it. The portal allows you to submit your code. And if your program is correct, which means if it produces correct answers for the problem sets that they have set up, then it'll say, yeah, this is accepted, congratulations. And you would have built a profile of the problems you've solved. Now, coming to your question, what language, it turns out it'll allow a bunch of different languages. So if you're a C program hacker, fine. If you're a C#, Java, Python, you name it, almost all these languages are okay. If you want to improve your skills on some other language, you're welcome to go and try that as well. So these portals are quite amazing. They are nicely set up. They allow a lot of flexibility. And this is very useful because it all depends on the training that you have or the training that you want. So language is really not an issue, but you need to get comfortable with it. If you want to be a competitive programmer, you want to improve your skills in at least one of the languages, and so it's a good idea to focus on one or two at this point and make sure that you have sufficient expertise. At this point, Python and Java seem to be clear winners. Java because you learned that in our early programming classes, and Python because it's somewhere up there just today I saw an email that said among the top 4 are Python, Java, JavaScript, and one more, I can't remember what it was. But these are your top 4 languages. if you know one, you should be it shouldn't be all that challenging to become reasonably good at one of the other languages. So I'd say focus on one, stay with it, and grow your expertise. Does that answer your question? Other questions? All right. So every Wednesday we'll be here. Feel free to come and join us. So let me start with some of the with what I have for you today. All right. As I said before, the focus of these sessions are problem solving. Do you want to come somewhere here and stand perhaps?
Let me just.
You guys can maybe help us make a roll or something over there. If you guys can move shift just a little bit.
Yeah. Yeah, so the overall focus of our sessions, as I said before, is problem solving. And problem solving really involves two things. One is finding the correct solution for the problem, and the other is finding an efficient solution. It turns out that these programming competitions focus on both. Without the correct solution, you have nothing. If it doesn't work, it's no good for anybody anyways. But it's also important that it's efficient. There are many problems for which you can simply write brute force algorithms where it'll work, it'll give you the correct answer, but after 43 years. So you don't want to wait that long. You better write efficient programs. And the way to do this is by looking at more and more examples. The general thing about efficient programming is again a set of skills that you learn over time. In general, algorithms as a domain is more of a bag of tricks that you acquire over time. When you encounter a new problem, you figure out which of these tricks you want to apply to that problem, and hopefully it works for you. There's also some skill in knowing that some approach is not working very well, and that you should change your strategy. These are all things that come by practice. I can't really teach these in class overall, but I can teach you how to think about this, how can get you started, and how to follow the path as far as you can go, and then figure out how to solve the problem. So let's start with some really simple problems that most of you have seen in your first programming class. And this is called find max, meaning find the largest. So let's say you're given an array of n numbers, yeah? And let's say you want to find the largest item in this array. Well, there's a simple solution for this, right? Most of you who have taken programming 1 know how to solve this. Yes? Yes? Do I have a yes? Okay. And how do you do this?
You have a max variable, and then you set a for loop.
Okay.
And it's a brute force
Right.
solution.
Yeah,
Then
yeah.
the for loop will go through all the elements of the array. If the element in the array is bigger than the max, then max is just updated and then
Right.
return the value
So,
of max.
what's your name?
Ryan.
Ryan. Ryan is giving me a solution for how he would program it. What I want you to think about is how you would solve the problem if you're not talking about a computer. Okay?
Is the array sorted?
I have not told you that, so you can't make an assumption. If it were, I would have said sorted array. Since it's not, we should assume it's not. It might be, but that's not something you're told. You want to think about this without having to think about variables and for loops and programs, because that's what will help you to think about this as a problem, not as a program. Okay? And that's a skill. It takes some time. Essentially what he's saying is, I'm going to run through the array and keep track of the largest I've seen so far. That's all. That's what he said. Now, yeah, he explained to me in terms of a for loop, which is way more useful if I actually want to write a program, but if I want to think about this conceptually, it's worthwhile to think about it the way I just described it, saying, I'm just going to keep track of the largest so far, okay? If I have a list of names that I gave you, if I give you the names of all the students here, and if I say who's alphabetically first, well, again, if I gave you a printed version of the names, you would kind of go through it and keep track of the one that came alphabetically first. So in a sense, it's useful to think about how you would do it by hand in order to solve the problem, which will help you in many of the problems, okay? So there's a simple solution, and the simple solution involves a simple for loop. Yeah, you have to hold on to a variable which keeps track of the best you've seen so far, the largest you've seen so far. And that's all it needs. So there's a simple iterative solution, meaning you iterate through the whole array. Now, there are a couple of things you should be thinking about at this point. Is this correct?
Yes.
Well, yeah, of course it's correct. I mean, it's a no-brainer, right? I mean, that's how you're going to tell yourself, yeah, of course it's correct. Why is it correct? Well, why is it correct?
It gives you your marks. It solves the solution.
How do I know it solved the solution? It solved the problem for me.
But it's not very efficient.
Well, let's not get to the efficient. Let's talk about correctness first.
Because we went through every possible value. And
That's right. We looked at every item,
biggest.
but did we compare everything with everything?
Not directly.
No, not directly. That's right. So actually, we could create an argument that says, yes, we actually sort of compared everything with everything, because if this is bigger than this and that is bigger than that, then we don't really have to compare A and C, right? Because it's obvious. So that kind of intuition is necessary in order to convince yourself that the algorithm is correct. And it's useful to think about why it's correct. It's useful to articulate this in your head, because that will help you solve other problems better, okay? So whenever the only answer you get is, it's obvious, of course it solves the problem, well, I suggest that you try and say this in words to yourself, or to explain it to somebody else, and that will help you to understand this better. And to understand that it is correct is a non-trivial thing. It gets harder and harder with harder problems. So somewhere you have to start, and this is a good place to start. Then comes the question, is it efficient? And in order to understand efficient, we have to talk about time complexity. Are there people who don't know what time complexity means? Okay, good. No hands were raised, so I assume that you heard of this somewhere in your programming classes. You need to write efficient programs. Otherwise, they take way too much time, and if they're part of a larger program, it's going to waste your time and someone else's time and someone else's money, and if you continue to write poor programs, you'll soon be out of a job. So we should be thinking about time complexity, and in this case, what is the time complexity for finding the largest value?
O of n.
It is big O of n, and the reason is, what's the reason?
It goes through all the values in the list.
Well, so we keep track of the largest we've seen so far, and we compare it against the next item, right? If necessary, we update it, so obviously it's big O of n. Now, if I think about how many comparisons I made, what would your answer be?
It depends.
Sorry?
n-1.
So you actually have to make n-1 comparisons. Is this clear? If there were two items, I would just make one comparison. I would know which is bigger. If I have a third item, I would make one more comparison, and I would have the answer, right? So the for loop stops at n-1 because it doesn't have to do the last iteration, right? So it's n-1 comparisons. Is this clear? Everyone okay with this? Yes?
Yeah.
No? Okay. So really the right answer is not even just big O of n, it's n-1 comparisons. Now, Let's talk a little bit about the implications of big O of n. How well do you understand big O of n? What does this mean? What is this big O of n?
It means the worst cases scenario.
The worst case is linear. Is that what you said?
Yes.
Okay, good. That's good. That is the correct answer. But I still question, do you really understand what that means? So we know, this is essentially what she said. She said that the time to solve the problem grows linearly with the size. Size of what?
The array.
Size of the array, right? Well, there is one other implication of this. What does it mean to say if something grows linearly with size? Anyone? Any other way to explain this to people?
It means the bigger the input, the longer it's going to take to get the result.
Okay, good. I like to think about it this way, and it's not that different from what you just said. I would say if you double the size, it should take you double the time. Okay, this is a more quantitative way of thinking about it. If I triple the size, it should be triple the time. If I make it 1,000-fold larger, it should take me 1,000-fold more time. That's what it means to be linear. That's what it means for the time complexity to be linear. And this implication is necessary before you understand what it means. Okay? The big O of n can be sometimes confusing. What is this thing with the big O? What is this constant? How do I compare two things where both of them are big O of n? It'll tell you that this statement is true regardless of what that constant is. It's always true that doubling the size will double the time that it takes to get the answer. What it also means is if I have to solve a problem with 100 million items, if my array has 100 million items, I don't need to experiment with 100 million items before telling you how much time it takes. I know it's linear. All I have to do is to experiment with, let's say, 1,000, and I would know the answer from there because all I have to do is to multiply it by the appropriate number, and I would have the answer because that's what this told me. And that's what it means to say when something is big O of n. So keep that in your mind. These are all useful concepts to go with. Sometimes the definition in the book can be intimidating and may not quite get you the right explanation for things. Clear? Okay, what else? The bigger question is this optimal? Is this the best we can do for finding the largest in an array of n items? This is a question. So here I'm giving you a list of questions that you should ask for almost every problem. Okay, first of all, is it correct? Is it efficient? Is it the best you can do? Well, there are actually a couple other questions you can ask, but let's get to that later. Is this optimal? Well, the algorithm we just described, which is keep track of the best you've seen so far and just keep looking at the next item and go through the whole list. And we did say that it was n-1 comparisons, right? Where's my little, come on. There you go.
Turn off the laptop. If he comes back.
Oh, he might come back, yeah. Is n-1 the best you can do? Yes, no, maybe? Yes? You think it's the best you can do? She thinks no. All right, let's question her. Why do you think it's no? Is it,
I think there are better approaches to this.
There are better approaches to this.
We can do
But
much
that's not a good
more
enough answer. Tell me why you think it's not optimal.
because we do not necessarily, we can find the largest number in the middle of the array, for example.
True, but
Which means that
remember the question we are asking it is this optimal in the worst case? Right? Because time complexity is always defined for worst case,
Worst case,
right?
yeah.
You know this. So, is it the best you can do? Worst case?
Oh, the worst case,
You guys all agreed with me, yes? Now you want to change your answer?
No, I just want to say that I think O of n, I think is the optimal because
O of n is fine.
because it could be like at the end, it could be at the middle, but we don't know. So
Okay, so that seems like a good intuition, but n minus 1, what do you think of n minus 1?
I have a general question.
Uh-huh.
So, when we use like, for example, if we use the built-in function of sort in Java or like any programming language, what is the time complexity of that?
That's an algorithm that it has its own built-in algorithm. Whatever is the time complexity of the algorithm of sort, that's going to be your time complexity. You can't just use sort and say, oh yeah, that was just one step. That doesn't work. You have to know what kind of algorithm was built into it. So again, think about this not like a program. Think about this in terms of how you're going to do it by hand. Okay, I give you a list of whatever 1,000 numbers, and I ask you, tell me what is the least number of comparisons I have to make in order to find the largest. I know how to do this in n minus 1. I know exactly how to do this with 999 comparisons because I have 1,000 items. But is there anyone on this planet who can beat this? And these guys are telling me the answer is no. What do you think?
I think we cannot do better than n minus 1. I don't see I don't see.
Right. So in fact, this is where we get stuck. We say, I can't think of a better one. But then there are lots of problems where some smart person shows up and say, I know, I can show you how to do this better. Yeah. And then you're like, whoa, I didn't think of that, right? We've seen many such algorithms and solutions. So how do you know tomorrow there's not going to be some bright 15-year-old who shows up and says, I know a better way to do this?
You could show like a mathematical proof or something. Don't ask me how.
That's where I'm heading.
Okay.
So there is a mathematical proof that shows that no one on this planet can beat n minus 1. Okay? And the argument turns out to be surprisingly simple. Here's how you go about this. Instead of thinking about this as arrays and finding largest, I'm going to think of this as a tennis tournament. Okay? So I have n people, and these n people need to organize a match, and I need to find the champion, the largest, the best, right? And you're free to organize the tournament any way you like. You could do this like Wimbledon does, where you do pairs and then blah, 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 or you could just go one after the other, or you can do whatever you like. Now, every comparison corresponds to what? Corresponds to a tennis match, right? So you're comparing two people. You're saying, go get on the tennis court and tell me who's better, right? Or which number is larger. At the end of that match, you know which one is larger, or which one is better, or which one is ranked higher. So the question is, how many matches do I need to organize? Now I'm the organizer. I have to pay for every match. I want to know how many matches I need to organize in order to find the winner, the champion. Okay, I'm saying the answer, the question is the same. Because you're finding the largest, there you're finding the champion. Now, I want you to think about it this way. In every match, two people play, and one person is, let's assume that one person wins and the other person loses. If it's Wimbledon style, or if it's a knockout tournament, the person who wins stays, and the person who loses goes home, right? So, if you want to judge the winner, how many people have to go home?
Oh, everyone except the winner.
Everyone except the winner. And in one match, only one person can go home. You can't send both people home, right? So therefore, What's the least number of matches I have to play before deciding on a winner? Well, I have to eliminate n minus 1 people before deciding on a champion. And therefore, this is the best I can do. And it doesn't matter how you do the comparisons, it doesn't matter how you write the program, it doesn't matter how smart you are. Because I have to eliminate that many values, numbers, which is the same as saying I have to elect a champion, right? Is this clear? Everyone okay with this? So therefore, this is the best you can do.
Can I ask a question? Can you do it by contradiction, by saying?
This
let's
is a
say-
contradiction proof. This is exactly a contradiction proof. It says that if you were to, I take that back. It's not this.
I was going to say like n minus 2. Let's say there's n minus 2 possible comparisons.
Right.
Then I can prove that I left one person out. I did not compare one person.
Perhaps, yeah. It depends on how you write the argument. It's possible. But in the end, this is a mathematical proof that says in every comparison, only one number gets eliminated as the maximum. And therefore, and I know I have to eliminate n minus 1 numbers to be the maximum, because I have to find the maximum, right? Everything else should be not the maximum. And therefore, all those have to be eliminated, and every comparison eliminates exactly one. Not less than 1, not greater than 1, not greater than or equal to 1, not less than or equal to 1. It's exactly 1. And therefore, I need exactly that many matches in order to decide on the winner. That's the best I can do. Of course, I can do silly things like do a round robin tournament if I want, okay? But those are all not so useful. I'm just doing wasteful matches just to please the crowd, but I don't need it in order to figure out the champion. Is this clear? So there is a mathematical proof. That's why this is optimal. All right? And this kind of optimality answers, proofs are not easy. I am not recommending this for every problem, but it's a useful exercise to think about this for every problem you solve, because it'll help you to think about how to improve your solution. Often your first solutions are not necessarily the best. You want to think about how these can be improved. And it turns out here, your first answer, your first solution was the best, and it could not be improved. Is that clear? So yeah, it's true that we've seen a whole bunch of other techniques that seem like, well, I should be able to do better here. But then this proof will blow all that away. There's no question about it. This is the best you can do. So go with a simple solution here, and it works. Now, this was what we call as the basic problem. Now, what am I trying to change next? Oops, sorry. I'm going to change the problem a little bit. This next problem is still finding the maximum, except that it's going to be what's called as a query version. Slightly different. Clear? Let's see what this problem is. So the first one was about find max basic. It's the same thing that you just saw. We know that there is a simple solution, and we also know that it's optimal. So we've done pretty well with the basic version. So now let's up the ante and look at a harder problem. This is called the query version. The query version is different how? It's different as follows. We're still given an array A with n values, all right? But we're given a query with 2 numbers I and j. All right, I'll give you 2 numbers, and your job is to output the largest value in the subarray between positions I and j. So A may be a big array, but I'm just asking you for the largest value within a small region. And it's a query that's separate from the input here. All right? Now, why are we calling this a query and why are we calling this an input? Well, there is a reason for this. Before I tell you the reason, how would you solve this? Well, what's the simplest way to solve it, let's say? Right? Go from I through j and find the largest, right? Naive solution, it works because it's correct. We know if that is correct, this has to be correct as well, right? So finding the largest in the locations I through j is not a problem. By the way, this shouldn't be a comma, this should be dot dot, I'm sorry, that was a mistake. So in the locations I through j, I can find the largest by simply scanning through that list. Now, by the way, you could say this is a, maybe let me not go there. So, the reason this problem is a little bit different is because we may have lots of queries. First time I may ask you between locations 3 and 7. The next time I may ask you between locations 5 and 13. I may then ask you for some other pair of locations and say, find me the largest in this pair. And your job is to just look at that part of the array and give me an answer. All right? Now, what I'm telling you is that the number of queries may be very large. Okay? So the size of the array, think of it as 1,000. And the number of queries could be super, super large. Million, billion, I don't know, whatever you like. So if for every query, I'm going to go and look through the array, am I going to do well? You're not going to do well. In fact, what is the time complexity of this?
O of n squared.
O of n squared. How did you get n squared?
You would have to go through every query and then like go through.
How many queries are there?
I don't know.
I told you
K,
there.
K, sorry.
K.
N times
So,
K,
sorry?
N times K.
N times k. Good. So really, the time complexity is n times k. And if k is large, this is going to drive me nuts. Think of it as setting up a website where you have some array of numbers, or let's say you have the heights of all the buildings on Calle Ocho going from, I don't know, downtown to wherever it goes to. Okay? So I have an array with all the heights of all the buildings along the way. And I say, find me the largest building between 57th Avenue and 97th Avenue. Yeah? And then again, there may be someone else who logs into the same website and says, I want the tallest building between some other pair of numbers. So the number of queries could be very, very large. And it's not connected to n. It could be way larger than n. And what we saw is that if we do this the naive way, like we did over here, the basic version, we're going to spend a lot of time. In fact, the time complexity then becomes big O of n per query, which is the same as saying it's big O of k times n. Okay? Now, can I do better? Because, well, the main, what's the main feature of this problem? How is this problem different from that? Other than the query thing?
Repeated work.
Repeated work, yes. On what?
If we're going from I to J, let's say 57th
Right.
to 97th.
No, I understood your answer for repeated work. I'm asking, it's repeated work on what? And my, well, maybe my question is poorly framed. What I'm trying to say is the following. Is that the array on which you're doing the search is fixed. So you are doing repeated queries, but the input is not really changing. Okay, it stays the same. And my thought is, shouldn't I be able to exploit that somehow? I'm asking millions of queries. In fact, I don't even know how many queries I'm going to make, but my array is fixed. Maybe what? There are there are 100 and whatever, 90 blocks on Chi Ocho, so maybe there are 190 numbers, so think of n as 200, if you will. And I give you pairs of numbers. Every time someone else gives you a different query, and your job is to answer that query as quickly as possible. So if efficiency is an important thing, your queries, your time complexity becomes dependent on the query. And this is not a good sign, right? So what should I do?
Keep track of the largest value at every point.
Okay, good. So, so here's a suggestion. I'm just repeating the problem. So this is, oh, I thought I fixed this, okay. So one idea is to keep track, remember your past queries. Really, this is what you're saying as well, right? So what if I try to keep track of the questions people have asked, so that if they ever ask me the same thing again, I could quickly answer this. The problem with this is that K is unlimited. In fact, K is very, very large, and trying to keep track of all these queries will drive me crazy, right? So, yeah, it's a possible solution, but it doesn't look like the best approach. And then even if I did keep track of all the queries, I have to go and search the darn thing and figure out what was that query again, and then figure out what answer I gave it. Yeah.
Start from I and J instead of start from I and end in J instead of starting from the beginning of the array.
I and J are arbitrary numbers, and you're saying what?
Is I and J within the array, right?
Yeah, you should assume that. Yeah, in fact, I
Okay,
did
so-
say that. I and J are between 1 and n, so they are within the array, yes.
So start starting from I and J instead of starting from the beginning of the array to the end of the array.
I think that was the solution that people had in the first place. That's the obvious solution, saying if your query is I and J, I start from I. If I'm trying to find the tallest building between block I and block J on Chi Ocho, I walk from I to J and I find and I report the largest, right?
Can I propose a solution?
You're going to tell me a possible solution? Okay.
One better than n squared is if in this case.
Well, it's not n squared. It's
N
I
to
see.
the
You mean
power
k? You're equating k times n to n squared.
Yeah,
Okay, fine.
n to
Uh-huh.
k. In this case, if we sorted it, then we could just return the index of j, and that's going to give us a time complexity of n.
If I sorted it, I would have the largest up there on top.
Yeah.
I don't know where it is in the array. And then the second largest, which could be somewhere else, and the third largest could be somewhere else. But I'm only interested in some range I through j. How do I know which one is the largest? How do I do the search? You still have to search, right? You still have to kind of figure out.
If the whole thing is sorted,
Yeah.
then you would just return j, assuming that's.
Remember, you're not searching for the values, you're searching for the locations now. I and j are locations, whereas you have an array of values. You were going to say something.
Wait, never mind.
This sounds a bit painful, but maybe, but maybe like keeping, for example, let's say you have like I is 1 and then j is 3, right? Then
Yeah.
we keep the max between these ranges and we like save it,
Mhm.
maybe using a hash map and then.
Yeah, forget hash maps.
Okay,
We don't
okay.
talk about hash
Okay.
maps in this
We
session.
save it, right? So
Yeah.
basically we can take these two numbers and then
Mhm.
we get up the solution. Then we can 1 and 3 and then 1 and 4. Then 1 and 5, 1 and 6.
Uh-huh.
And since n is,
Basically keeping track of the range.
yeah, of every single value.
Of the past queries.
Not just the range, but the answer to that.
You're keeping track of the queries and the answers that you gave before. Is that how I should understand what you just said?
Yeah, basically you do that
Yeah.
work and then you save it later so you can pull it out quickly.
Okay. Did you have something else in mind, or you all said the same thought? Okay. Yeah.
You could store the largest number for each index from 0 to that index.
Mm-hmm.
And then you could also store it from 1 to each index, because when you go to the, like, if you get all the largest numbers from 0, then to
Okay.
get the largest numbers from 1, you just have to check
Okay.
if that number is in like was 0, like was before that range.
Yeah.
Or you have to update it, and then you can get like from 2 and then from
So
3.
is that part of the pre-processing, or is that part of how I'm gonna answer
the
queries?
pre-processing, and then each query will just take
We'll just do what?
constant time.
Okay, all right. Okay, we'll get back to you in a couple minutes. Any other thoughts? Yes.
So we could go through the array and then like keep track of the largest value at that current index, like from what we've seen before as well.
Uh-huh.
So if we're at 0, whatever that value is would be the largest there, and then when we get to index 1, we would compare what we had with 0 and what's at index 1. and keep
Okay,
track
let
of the
me
value.
show you this example. Here's my array, simple array, small array. And I say, hey, find me the largest between 3 and 5, or 4 and 6, or 2 and 9. You think you can answer this quickly, based on what you just said?
Yeah. I think I could,
Yeah? How?
by looking at.
By
No, okay.
So you should think of this as 1,000 items. I'm just giving you a small example, right? So you can't look anymore. You have to compute now.
I like this
So-
idea.
You like his idea. I'm gonna come back to it in a short
Can we
bit.
create like a new array?
Uh-huh.
For example, we do the first comparison, we put it on the new array, the next one, blah, blah, and then we just do a search inside
To find the largest within what?
inside the new array.
But what
That
is
would be
new?
shorter, a lot shorter.
I'm not quite following you. So you have this array. You're saying I'm going to,
I create a new array.
for the query or for the pre-processing? So these are two different things.
Okay. Oh, well,
Right?
yeah, I was trying to find a solution.
Yeah. Any other thoughts before we talk about a possible solution?
I don't know if this is what you meant, but every time you have a query, instead
Mhm.
of keeping track of every IJ and the max within that IJ, you keep track of the known max from, I don't know if you meant to say 0 to that point.
Yeah.
But to go with your example, let's say 5 to 7, I already computed the max.
Up to
That
7.
has to help me in the next query. I'm not
Yeah,
gonna
no,
redo
so
5 to 7.
let me hold you back, because you're getting into advanced stuff, and I need to catch up everyone to the earlier solution. So I will come back to that and ask you again. But is the problem clear to everyone? Now, you don't really care so much about how much time it takes to pre-process, because that thing is sitting there. It's okay to spend a little extra time to pre-process, but when people ask me queries, I shouldn't be sitting there doing computes. I shouldn't see that circle that goes around when the computer is still figuring out the answer. I want answers like that, right? So query time needs to be fast. Pre-processing time can be large. And so the question is, how can we do this? And I forgot which slide I was on, so perhaps I was here. Right, so clearly we all seem to understand that the time it takes for each query turns out to be big O of n. And if there are k queries, it'll take me k times n. If k is very large, this whole thing kind of blows in my face. So I don't want to spend linear time, because this is not the same old situation where I cannot do any better. Because many of these queries have come before, I've seen many of these items before. It doesn't make sense for me to go and spend the same amount of time for every query. And secondly, the time it takes for me to answer a query will really depend on how far I and J are, right? So that's why this naive solution is no good. And so therefore, it shouldn't be hard for you to be convinced that the naive solution is not the optimal. And so we did talk about pre-processing, and we said that the simplest pre-processing idea is how to remember past queries, but then this has a problem as well. And I will talk about this because remembering the number of queries in the past can be very, very large, and keeping track of those queries could be way too expensive. Now, that's why that may not be such a great idea. Instead, what we want to do is to pre-process the input, meaning the original array, and we want to do this before looking at any of the queries. And remember, you're allowed to spend as much time as you want doing that pre-processing so that you're ready for the queries. And this makes sense because the original array is fixed, it never changes. Okay, it's not a dynamic array. Some of you who have taken data structures have seen examples of dynamic arrays, and this one is not. This one is a static array, it's fixed in time, and so therefore it makes sense. But now that we understand this much, the question is, what am I storing in order to make the queries as fast? And this is where we come to your solution, and right. So we said all this is no good. So the new idea, and I'm going to rephrase what you just said, the new idea is to pre-process the answers for every possible query. Okay? Figure out beforehand what the answers are, and then when the query comes, it should just be as quick as snapping your fingers. Now, how do we do this? And how do we store the answers? That's where the trick is. Okay? So, what I'm going to show you here is this. Well, here's the. Again, I have way too many unnecessary clicks. So, so it turns out that in order to store all possible answers to all possible queries, we're going to use a data structure. In fact, we're going to use a simple array, and this array is going to be a two-dimensional array. And by now, some of you may have figured this out. And this array, let's call it B. If you look at the ith row, jth column, it should answer the query for the query I and j. And remember, your I and j have to be between 1 and n. So therefore, this table should have all possible answers. All you have to do is to go and look it up. Okay, so then the question is, how good is it? So we saw this example, and the process 2D array is going to look like this. So from this array, I could potentially build this pre-processed array so that this whole thing is ready. You just have to ask me a question, and I'll give you an answer. So if you say, I want to know between 2 and 7, I go to the second row, 7th column, and I tell you the answer, it's 41. Okay? I don't have to think about this, it's just a lookup. In the end, it's just reporting an answer from a lookup table. So your queries are constant time, which is what he said. Is this now clear? So reporting the answer becomes just a lookup, and therefore is constant time, but pre-processing is very expensive. Now, how expensive? And that's what we're going to look at next. Everyone clear about this? Yes? Okay, anybody needs more explanation here? All right. So so here is how you fill in that table. So then we have to now talk about how to construct this table, right? And we got some clues as to how to do this. And essentially, we're going to try every possible start point, every possible end point, and look at that portion of the array and find the largest in that piece of the array. This is the simple pseudocode for building that array. The question is, how long is this going to take, and what's the time complexity of this? So in order to answer that, I need to know how big this array is. By the way, that array, why did I only fill 1/2 of the array?
Because the first row is from 0 to n, and then from 1 to n, and then from 2 to n.
So,
So you don't, in the row after the first one, you don't include the first value and then the second value.
J has to be greater than.
j has to be bigger than I,
Yeah.
right? And so therefore 1/2 of the array has no information that's of use to me. In fact, if j is smaller than I, it's not even a query, right? It's not a valid query. I can throw it out and say, hey, ask me something harder, right? Is that clear? So therefore 1/2 of the array is of no matter to me. In fact, I can put in zeros there or infinity or just a message saying this is not going to work for me. So how many entries are there in B that need to be filled up? Yes? How big is the array B?
P multiplied by Q.
P and Q are placeholders. It's a for loop variable, right? So that's not your answer. What's the answer?
N squared divided by 2.
Correct. So it's n squared if you're going to fill up the whole table, and it's roughly half because half the matrix is empty, right? So it's roughly n squared over 2. Let's just say it's big O of n squared. Is that clear? So the time complexity, well, before I even get to time complexity, I want to know how many entries there are that I have to fill. The problem is that depending on the entry, it's going to take me different amounts of time to fill. So therefore, I have to kind of figure out what's the cost of doing that computation B of P comma Q. And the problem there is in order to compute B of P comma Q, I have to know what's the largest from position P to Q, right? And how much time will that take me? Well, it takes me Q minus P time, roughly speaking. But Q minus P, because we don't know what P and Q are going to be, it can be very, very large, and therefore it can be as bad as big O of n in the worst case, right? And so in the worst case, because each of these can be big O of n, there are two nested for loops, so therefore building this table can take you n cubed time. Is this clear? This is n, and this can be as bad as n. Fine? So this n cubed time makes it very, very expensive and not a great pre-processing step for the problem. And so then we should be asking, can we improve the pre-processing time? By the way, assuming that we go through with this n cubed, what is the time for k queries? It's just k because it's each time I'm just looking things up, right? So it's only a constant time to, so it's really k plus n cubed if you decide to add the pre-processing time. If you don't, it's just order of k. Is that clear? So all this is great if k is very, very large, if it's larger than n cubed. So if n cubed is big O of k, which means if k is an upper bound for n cubed, then you're okay. Otherwise, you're probably not doing so well. Is this clear? So what if k is smaller? Then I should look for better ways to do the pre-processing. That's really what it tells you. So if the pre-processing is faster, then I could do something better. And it turns out that I can improve the pre-processing. Oh, I need to fix this. So we said that this is our pre-processing algorithm. In order to compute this, it turns out that, I know my time is running out, so I'm going to make this fast. In order to compute B of P comma Q, I'm going to use the previous values. Essentially what it says is in order to figure out the largest item between locations P and Q, I don't have to look at this all the way again because I already solved the largest item between P and Q minus 1. So now I have just one more item, and I should be reusing this information. So it turns out you can write a smarter code for this, and the simple recurrence or simple statement that you get is, in order to find the largest item between P and Q, I only have to take the largest item between P and Q minus 1 and look at the last item that I haven't looked at and find the larger of the two. So one extra comparison, and I can fill in one extra item. So really, in order to fill this matrix B, I can do this very, very quickly. In fact, I can do this in, I can fill each entry in roughly constant time. And then if I want to solve K queries, now it becomes K plus N squared. All right. So again, I can go through this argument and I say, if K is very large, in fact, if it's between N squared and N cubed, I'm in great shape. But what if it's less than N squared? Then I'm in trouble. So I need better pre-processing, and that's a lecture for another day. Okay, any questions for me? So what's important here is a slightly different model of a problem. Here we are not trying to solve an algorithmic problem. We're trying to solve what's called as a query style problem, where we are allowed to pre-process things as quickly as possible in order to solve the problem. Now, over here, in the end, queries were answered in constant time, but there was a serious drawback to the solution, and the serious drawback is that we were using a ton of space. In this case, it was using a 2D array. If the array has 200 items, then n squared would be something like 400,000. And so that's a lot of, sorry, 40,000, is it? That's a lot of space. With larger arrays, this becomes harder and harder to manage. And so therefore, we need better solutions. And the better solutions takes us to binary search trees and so on. So we'll do that some other time. For now, what we need to understand is that this is a different model of problems. This is not a dynamic problem where the array keeps changing. The array is static, but we have very, very interesting queries that we have to answer. And these are common questions when you're trying to solve, trying to say build a website, or trying to solve some dashboard problems, or trying to solve some analytic problems where queries can come over the internet and you have to solve them. Okay, so it's a nice paradigm for a lot of interesting harder problems, but this is a good place to start. So we went from very, very easy problems all the way to fairly hard problems. And again, over here, the important thing is to understand that there is something called where is that? Yeah, so this was the general approach we took, and it's a good idea to see this. The general approach we took was we pre-processed the input. We were allowed as much time as we wanted. We created a data structure which would help us to answer queries quickly. And then for each query, all we did was to say how we're going to look up the answers in this data structure. The complexity involves both the complexity of pre-processing and the complexity of query. You have to decide based on your application